Hello, I extend warm welcome for my next discussion, that is on Hartnell governor. Hartnell governor I have introduced you in my previous class, and we all know that Hartnell governor is also a centrifugal type of governor. It is also a loaded governor, and the loading is in the form of spring. Okay, we have a helical spring over the sleeve of the Hartnell governor, and depending upon the position of the sleeve, this helical spring is going to be compressed by different amount, and accordingly we have different amount of load on the sleeve. That is why we have a Hartnell governor, which is a variable loaded type of centrifugal governor, I can say. So the sleeve is supported by what is called as two bell crank levers, one on either side. So each bell crank lever is hinged on a fulcrum, so on a skeleton, and that skeleton is placed over the spindle of the governor. So when the governor spindle rotates, the skeleton of the governor rotates along with the bell crank lever, and the bell crank lever, so as normally we have it, it has two arms, two parts, and one arm is called as the sleeve arm, the other arm is called as the ball arm. So at the end, say, of the ball arm, we have a ball, and the ball also will be revolving at a constant radius whenever the load is constant, and that is the one which is introducing the centrifugal force, and depending upon the change in the speed, we have different centrifugal force, and that will make the sleeve to move. Okay, so bell crank lever. So if I just indicate it something like this, say the bell crank lever of the Hartnell governor is usually 90 degrees, the two arms are 90 degrees, and this arm and this arm, okay, they are single part as if they are welded like thing. Okay, this is what I mean, this is how, okay, so we have here a ball arm, and there is a roller. This arm is also called as a roller arm, and this arm is called as ball arm, and usually the ball arm is almost vertical, and at the most it may go like this or it may become like this. Therefore this also is called as vertical arm, and usually this is horizontal, and this is also called as horizontal arm. Sleeve arm is horizontal arm, sleeve arm, roller arm. These are the different names. Okay, so now whenever this moves, this is hinged at this point. So this we call it as the fulcrum. We have a hinge here. Okay, we have a hinge point, pin joint, we hinge it. So this arm can move. Say it may occupy this position, say this is another position, and similarly the perpendicular, this may be another position. Okay, so now if this is the ball and the sleeve arm, I have shown purposely an extension, a larger distance. Okay, so now please remember, so since the angle between these two arms is always 90 degrees, whether it is in this position or in this position, and whatever is this angle, the same will be the angle here. Or in other words, if I draw a triangle here, this triangle and this triangle, they are similar to each other. This concept we are going to use it later on during the analysis. Okay, I hope you understand. Before I go to the analysis of the Hartnell governor, one more small thing. And suppose if I know that I have a spring, a helical spring and a compression spring, and say like this, it kept over this, and say it is not of the free length and it is already subjected to some load. I call it as say S1. S1 is the load now, and it has already undergone certain compression, and let me call it as a delta 1. So S1 and delta 1, and then I have what you call as one more term, what is called as stiffness of the spring, and the relationship is S1 is equal to K multiplied by delta 1. So the spring force is equal to stiffness multiplied by the compression. Okay, the force is S1, and right now, and now I further compress it and I bring it here. And that I know, and say this is delta 1, 2. Let me call this as second position, and this is the first position. And I have further compressed the spring by an amount delta 1, 2, now the force, I call it as S2. S2 is the force, and I would try to know what is the relationship between S2, S1, delta 1, 2, K, etc. So I would like to find out. So this S2, do you agree that it is more than S1? Since the spring, depending upon the compression of the spring, more the compression, more will be the spring force. So compared to the position 1, position 2 has undergone further compression. Therefore, S2 is more than S1. Therefore, S2 is S1 plus. Okay, plus how much? So the spring has been further compressed by an amount delta 1, 2, this distance. Therefore, this will be equal to K multiplied by delta 1, 2. So S2 is equal to S1 plus K delta 1, 2. This is what? This also I am going to use in my analysis later on. Okay, I hope. Okay, Hartnell governor, okay, analysis I would like to go ahead. And before I go ahead, I would like to introduce some of the terms. The notation say MB, very common term, and which I had used it in my Porter governor discussion also. So MB is mass of each ball. Mass of each ball, of course, is in kg. Then I also have what is called as the MS, mass of sleeve, okay, which is also in kg. Sometimes when we start solving problems, okay, in numericals, and sometimes they don't mention anything about the sleeve of the Hartnell governor. In that case, I can assume conveniently MS as 0. Otherwise, sometimes it may be given what is the mass of the sleeve. In that case, we have to take it. Okay, therefore, I would like to have a general discussion which shall involve all the things. Therefore, I shall assume that MS also is there. MS is the mass of each sleeve. Okay. Then I have something, these quotations A, okay, this is nothing but the length of sleeve arm. A is length of sleeve arm of the belt crank lever. Okay, this is also called as length of the horizontal arm. Okay, length of the roller arm, all these mean one and the same. Then I also have what are called as B. So length of ball arm. So this is also called as the length of vertical arm. Okay. Then I have one more thing, notation C. C is the distance between fulcrum of bell crank lever. Okay, I have said the distance. So I have identified only one point now. Distance between fulcrum of bell crank lever and axis of and governor axis. Governor spindle axis. Okay, ABC. Those things I call them as ABC. Okay, all these values, whatever I have mentioned so far, they don't vary with the position of the sleeve. They are independent of the sleeve position, and these are the common terms I am going to use: A, B, C, and MB and MS. Then I am going to use some of these terms, what is called as R in general. R I use for radius of rotation of the governor balls I use, and so I may call it as say R minimum. The meaning is the radius of rotation of the balls when the sleeve is at its lowest position, that I call it as R minimum. Then I may also have what is called as R mean. I shall introduce a term what is called as R mean. So R mean, which is R, basically the radius of rotation of the balls when the ball arms are parallel to the axis of the governor spindle, or in other words, when the ball arms are exactly vertical, that time what is the radius of rotation of the balls, that I call it as R mean. Then I may also call it as R1, R2. They are nothing but there are some rotation, radii of rotations of the balls. Okay, at some position of the sleeve, not at the lowest position, not at the highest position, in between R1 and R2. So I shall also call it as R max. So these are the different notations I use depending upon the situation I would like to describe. Please remember, R mean radius of rotation of the balls corresponding to the minimum position of the sleeve. R max, radius of rotation of the balls corresponding to the maximum position of the sleeve. Radius of rotation of the balls when the ball arms are exactly vertical or sleeve arm is exactly horizontal, that mean position. And R1 and R2 are in between. The ball is not vertical, ball arm is not vertical, but it is not corresponding to the minimum position or maximum position, some positions. So this is one set of notations what I use, and corresponding the speed, if at all I want to mention. Okay, I call it as say omega minimum, then omega mean, then omega 1, then omega 2, and omega maximum. Okay, these are all equilibrium speeds with the friction force equal to 0. So friction force is equal to 0. When you take this, then I call these as the equilibrium speeds. A similar things you shall happen when you take friction into account, that I shall mention a little later, according to omega minimum dash, omega minimum double dash, like that you are going to have on every position of the sleeve. When you take friction into account, then you will have different speeds. Then you shall also have the corresponding sleeve, the spring force. The spring force I shall mention it by the term S, capital S I shall use it. S is the spring force corresponding to the minimum position, I call it as S minimum. Then I have what is called as S mean. Then I have what is called as S1. Then I also have what is called as S2. Then I have what is called as S max. Okay, so one more term I would like to add here in this category. What is this? Independent of the position of the sleeve, that term is what is called as K. The stiffness of the spring, which is normally expressed in Newton per meter or Newton per millimeter, Newton per centimeter. Okay, I shall use in the numericals Newtons per meter always, and all other dimensions I shall take lengths in meters. Okay, so now I also have, say something little more. I would like to have what is called as the displacement of the sleeve. So when I say displacement of the sleeve, it is always between the two positions. Okay, between the two positions, how much sleeve moves, that I call it as sleeve displacement. So I shall refer the sleeve displacement by the term x, depending upon the positions. Okay, so then I have to mention two positions. Say if I call it as x minimum, maximum. So between minimum position of the sleeve and the maximum position of the sleeve, what is the sleeve displacement? This is what I can call it as maximum sleeve displacement. Okay, similarly I may mention what is called as x minimum to mean. X minimum to mean. The meaning is the sleeve displacement from minimum to mean position. So I hope you understand mean position. What is the meaning of mean position? Mean position of the sleeve when the ball arms are parallel to the spindle axis. That position I call it as mean position. Okay, x minimum. So like that. So I shall have x1 mean. What is the meaning of that? Sleeve displacement from mean to position 1. Similarly, I may have what is called as x2 mean. Okay, sleeve displacement from mean position to position 2. This is what I call it as. These are the different terms I shall use in my discussion. I hope you all are familiar, understood? Okay, now what is the relationship between S maximum? S maximum is equal to S minimum. Okay, S maximum is the spring force corresponding to the maximum position of the sleeve. So S maximum is S minimum plus, it is more than that. It is K multiplied by X times minimum to maximum, whatever is the sleeve displacement. This is the relationship. Similarly, S mean, you all agree that it is more than S minimum? S minimum is S minimum, S mean is S minimum plus K times X minimum to mean. Similarly, if I want to know what is S1, S1 with respect to S mean, S1 is S mean with respect to, so if S1 may be more than S mean or S1 may be less than S mean depending upon how much is the compression. So whether with respect to the compression of the spring with respect to this portion, if it is further compressed, then this will be more. If it is loosened now, in other words, the compression has been reduced, in that case this may be less. So S1 may be more or S1 may be less than S mean. So assuming that it is more, in that case S1 is equal to S mean multiplied by K into X1 mean. Okay, it may be plus or minus depending upon, so yeah, whether this is positive or whether this is negative. Okay, so all these things I wish you to really understand. If you have any doubt, please ask me. Or ask me and you can stop and disturb me and then get it clarified. All these things, if you have understood, then the analysis is going to be very simple, very smooth, I can say. Okay, I hope you have understood it. Okay, so if there is any difficulty, please stop me and ask me. So now I shall go for what is called as analysis of Hartnell donor. Okay, one important thing I would like you to understand. Please listen to me carefully and observe the analysis of Hartnell donor. So unlike in Porter governor, we don't have anything called as a ready-made formula. So in Porter governor, we went through the analysis of Porter governor, and incidentally we ended up with a formula. And that formula we used it to solve all problems of Porter governor. But here, unfortunately, we are not going to have like that. So I shall only demonstrate the method of analysis, and this method you have to apply it, and without using any ready-made formula. So go through the problem, read it, understand it, make the sketch, and write the equation. That's what you are going to do it. Okay, so I shall understand. I shall go through first one. The first one, Hartnell governor. In short, I shall write it as HG. Hartnell governor analysis for mean position. So all the time so far I was talking what is mean position. This I am going to demonstrate it now. What is mean by mean position? So what is mean position? When the ball arms are parallel to the axis of the governor spindle, that position I call it as mean position. Okay, so I shall draw the diagram. Okay, let me assume that this is the spindle axis. Okay, I would like to analyze only half of the governor. I shall be taking it, and I shall assume the next question. So this is what I call as, what is this? The fulcrum of the bell crank lever. Fulcrum of the bell crank lever. The distance between the axis of the spindle and the fulcrum of the bell crank lever. This distance I have, as per my notation, I have called this as C. This is C. Okay. So now each bell crank lever you can draw. So bell crank lever, as we know that it has two arms. This is one arm and the other arm. Usually the angle between the bell crank levers, two arms, is 90 degrees. And so this is the sleeve arm, or what is called as roller arm. You have a roller here. Of course, the sleeve, this roller is supporting the sleeve. The sleeve will be above this. That I am not showing it. And here you have what is called as the ball. Okay, let me mention some of the dimensions. What is this? This is the length of the ball arm. As per notation, this is what we are calling as B. And this is the length of the sleeve arm. This we call it as A. We shall call it as A. Okay, and it is rotating at a radius r. This distance is what we are calling it as radius of rotation, and this we are calling it as r mean. This is r mean. Okay, now this is rotating at a speed omega radians per omega mean. The speed is omega mean radians per second. This is the speed. The balls are revolving. Okay, because of this we have various forces. So let me show. So I have one force here. This is what I shall call it as the centrifugal force, which is equal to mv into omega mean square into r mean. This is the centrifugal force. Then I also have, okay, this is one force. I shall just show the force in a different color. Okay, this is one force. Then I have another force, the weight of the ball, and this is equal to mv into g. Since this ball arm is right now vertical and this weight also is passing through the fulcrum of this bell crank lever. Okay, then I also have a force here. Okay, can you tell me what is this force? Okay, what all things that are acting? Please remember, this is the sleeve. This is connected to the sleeve, and over the sleeve you have a spring. You have something like this, which I shall rub it. This is the sleeve, and you also have a spring. So the weight of the sleeve is acting here, and the spring force also is acting, and half of that is coming here, and another half is coming here. That's what I am going to display. So therefore, the force is ms into g. This is nothing but the weight of the sleeve, dead weight of the sleeve, plus s mean, because this corresponds to the mean position, s mean divided by 2. This is the force that is going to come here. Okay, so all the three forces that are coming, that I have indicated. Now always we take for anything, whether in this position or any other position, the moment we are going to take, as the moments are all balanced, right? Because these balls are revolving at a constant radius and they are not moving outside, they are not coming inside, and therefore the balls are in an equilibrium state. Therefore, I can apply the equilibrium condition, and I am going to take moment about the fulcrum always. Okay, so the moment due to this centrifugal force is in the clockwise direction. The moment due to this weight mv into g, so we don't have any moment because that weight is passing through the fulcrum itself. Then we have another, the moment due to this force about the fulcrum is in the anti-clockwise direction. Okay, the total moment in the anti-clockwise direction, that is nothing but mv into g plus s mean divided by 2 multiplied by a. So this is the moment arm. A is equal to then mb into omega mean square into r mean. This is the force multiplied by, this is the moment arm, that is equal to that multiplied by b. This is the equation, and so some of these things may be unknown and some of these things are known, and this is how you are going to relate the unknown thing to the known thing. Okay, knowing all this substitute, and this is what I am going to get. So this is what I call it as Hartnell Governor analysis for mean position, of course, without taking friction into account. If you take friction into account, then this mv into g plus s mean plus or minus the friction force divided by 2. Then accordingly, if you don't take, it is omega mean. If you take minus friction force, then omega minimum dash. If you take plus friction force, then omega minimum, omega mean double dash square. That will be the change. Anyway, right now I am making the analysis without taking friction into account. So knowing the friction into account, that analysis you already know it, and therefore it is not going to take much time. Okay, I hope this is clear. Now I would like to move on. The second one, I shall rub this. The Hartnell governor analysis, for one more position I would like to make it. So Hartnell governor analysis, this I shall make it 2, the position 2. Okay, Hartnell, second analysis, Hartnell governor analysis for, it is not for the mean position now, for radius equal to R1 I shall call it. For R equal to R1 and say R1 is greater than R mean. R1 is greater than R mean. For this, how does the analysis simple? Okay, let me go through the diagram. Now again, this is the, what is this? Governor spindle axis. Governor spindle axis. So immediately I shall represent something. What is this? This is the fulcrum. Okay, I shall represent what is this? This distance. This distance is C. Okay, so now I shall draw the ball arm, and I know that the balls are revolving at a radius R1, and R1 is greater than mean radius. Therefore, the ball arm is something like this. This is the ball arm. And perpendicular to this arm, you have what is called as the roller arm. This is the roller arm. And this distance is what is B. And this distance is what is A. And I know that this distance, what is this? This distance is what is R1. And what is the speed of the governor now? Speed of the governor is omega 1 radian per second. Okay, I would like to relate some of these with respect to the mean position. Therefore, I shall draw a diagram corresponding to some of these with dotted lines. I shall draw. So do you agree that this is the position of the ball arm corresponding to the mean position, and therefore this distance I shall call it as what is called as, what is this? This is R mean. And similarly, okay, this is corresponds to what is called as the position of the sleeve with respect to the mean position. Okay, so now, so I shall draw a vertical line here, and can you tell me how much is this distance? This is R1 and this is R mean, therefore this distance is R1 minus R mean. Okay, so now I shall show the different forces that are acting. Okay, I have a centrifugal force. I shall show it by different color. Centrifugal force, let me write down how much mb. It is omega 1 square R1. This is this thing. Then I also have what is called as the weight of the ball mb multiplied by g. Please remember, it is along this vertical line. Now it is not passing through the fulcrum. I just draw a horizontal line here. Then I also wish to show the force here. The force again, what due to the weight of the sleeve, due to the spring force. Okay, so weight of the sleeve, that is ms into g. So what is the spring force? This I am calling it as position 1, and therefore let me call it as S1. mg plus S1 divided by 2. Okay, so now again, as usual, I am going to take moment about the fulcrum, but before I take the moment, so I shall write down how much is this distance. This distance I am calling it as A1. And let me call this distance. What is this? This I shall call it as B1. Okay, so what is this distance? from here to here. This was the main position of the sleeve. This is the position of the sleeve corresponding to position 1. So what is this distance? This is the sleeve displacement. Sleeve displacement between position 1 and mean position. This is what I had called it earlier. This is x1 mean. This is what I had called it. X1 mean is the distance between position 1 and mean position of the sleeve. Okay, this is what I call it as x1 mean. Okay, so now I shall take moment about this fulcrum and I shall write down. Before I go to write down that, so let me check what are the directions of the moments due to various forces. This force will produce anti-clockwise moment about this. This mb into g will produce clockwise moment. This mb omega square around centrifugal force will also produce clockwise moment. There are two clockwise moments and one anti-clockwise moment. Okay, let me write down the anti-clockwise moment first. What is that? ms into g plus s1 divided by 2 multiplied by what? Multiplied by a1. The arm distance is a1 is equal to mb into g multiplied by what is the perpendicular distance between this and this? That is nothing but this distance. That is nothing but r1 minus r mean. r1 minus r mean plus one more moment. What is that? mb omega square omega 1 square into r1 multiplied by what is the moment arm? The moment arm is this distance. That is multiplied by b1. So this is the equation. But there are so many unknown things here now. I have a1, b1, which I don't know. I would like to find them. And so what is this? So I would like to compare this triangle, whatever this triangle, and one more just dotted right, and this triangle. I hope you agree that both of them are similar to each other. Therefore, I would like to make use of this. What is this? x1 mean. x1 mean divided by this, that is nothing but a, is equal to this distance, that is nothing but r1 minus r mean divided by b. This divided by b. Okay, from this I know what is the relation. x1 mean is how much? x1 mean is a divided by b into r1 minus r mean. Okay, I know this distance. x1 mean is not unknown to me. So I know a and b. For a given coordinate, they are all constant. r1 is given. This is the new radii, and r mean also is known, and therefore all these values are known. Therefore I know x1 mean. It is not unknown to me. Now I would like to relate what is S1? S1 with respect to the spring force with respect to the mean position. Okay, so now with respect to the mean position, the spring has been further compressed. Therefore S1 is more than S minimum. S1 is S minimum plus how much more? K multiplied by x1 mean. x1 mean. K multiplied by x1 mean. Okay, that will give you what is the additional force in the spring over more than not mean minimum. It is S mean. S1 is equal to S mean plus K into x1 mean. So therefore S1 is also not unknown to you. You know this, and A1. Okay, now let me find out what is A1. A1 is nothing but this distance. This distance is equal to square root of this square minus this square. So A1 is equal to square root of A square minus x1 mean square. That is how we can find out A1. Similarly B1. B1 is this distance. You know this, that is B, and you also know this. Square root of this square minus this square will give you this square, and therefore B1 is equal to square root of B square minus R1 minus R mean whole square. This is how you can find out B1. So therefore you know S1, you know A1, and you know B1, and therefore you can relate this. Usually it is a combination, the previous mean position analysis and write down another equation for this. You may have to solve simultaneously or sometimes. So make use of the data whatever you have found out from first one, and then use it here and find out the unknown. Okay, so this is how you are going to analyze. And similarly for R equal to R2, when R2 is less than mean position, the whole arm has come this side. Okay, and that I shall show you in the next class analysis, and also I shall take up one numerical problem in the next class. Okay, if you have any doubt, anything, please let me know, and so that I can answer your doubts. Thank you. All the best.